So when we're working with composite functions and trying to take the antiderivative, what we're going to need to use is something called the substitution method. So this can take some practice in terms of identifying what pieces we want to work with, but the best piece of advice is that when we make this substitution for some variable u, we want to look for the inner part of a composite function. So what that might look like is like having a function raised to an exponent. When we have some function in there, let's say, well, for the sake of simplicity and looking ahead at our example, let's say it was 2x to the fourth plus 7. And we were raising it to some exponent, like we see an exponent of 7 there. In terms of a composite function, this f of x would be the inside function, and this exponent on the outside would be our outside function. So what's going to be helpful is when making our substitutions, we want to label our variable u as the inside part of the function. Now it's not always under an exponent. Sometimes it can be within an exponent. It could be under a square root symbol. It could be in a denominator. We're going to look at all sorts of scenarios here. But what we want to relate as we do this is that we're going to have some variable u that we're going to evaluate and the derivative of u. We want to use those two pieces together so that we can rewrite our integral in simpler terms, so that then we can just use our rules of antidifferentiation that we learned in the previous weeks. So let's go through some examples here. It does just take practice of how to identify what u is going to be and what du is going to be. But then from there, it's just using previous rules. So let's say we want to evaluate the antiderivative of 8x cubed times 2x to the fourth plus 7 raised to the 7th power dx. So if I'm thinking in terms of composite functions here, like I was saying above, this 2x to the fourth plus 7 is trapped under that exponent of 7 there. So this would be an inside function and this would be an outside function. So let's say I let u equal 2x to the fourth plus 7. Then what I want to do is evaluate the derivative of this. So what I'm going to do is take the derivative of both sides of this equation, which taking the derivative of u will leave me with du. And then I'm going to take the derivative with respect to x. So 2x to the fourth is 8x cubed. And then that positive 7 turns to 0. And then because I'm taking the derivative with respect to x, I'm going to put a dx at the end here. Now, at this point, this will tell me whether or not I'm on the right track with choosing my pieces here. So that 2x to the fourth plus 7, that's going to substitute real nicely. And then when we took the derivative, this 8x cubed lines up perfectly with that 8x cubed up in the integral. And that's what we want to see. We want to see this connection of a piece that's relating to u and this piece that's relating to du. Now, we have pretty much all of our pieces accounted for here, so we can start making our substitutions. So u is equivalent to 2x to the fourth plus 7. So what we can do is where we see 2x to the fourth plus 7 in our original integral, what we're going to do is replace it with u. So I'm going to take the antiderivative, and we're going to substitute in u, and then it's going to be u to the 7th power. Now, that takes care of the 2x to the fourth plus 7. That also takes care of that exponent of 7, since we put that on top of u. Now, the other pieces that aren't accounted for is the 8x cubed and the dx. So the 8x cubed dx, what we see is how that can be replaced with just du. So I'm going to have as the antiderivative of u to the 7th du. So with those two pieces, I've now covered that entire integral. I've just replaced things in terms of a variable u, but everything's accounted for. The 8x cubed is part of du, 2x to the fourth plus 7 is u, and then we have our exponent of 7 on u, and then the dx is part of du. So now what we can do is pretty much ignore everything over there and just focus on what's the antiderivative of u to the 7th du. And with that, it's just our power rule for taking the antiderivative. So it would be u to the 7 plus 1, which is 8, divided by 8. And then this is indefinite, so we'll have a plus c. So in terms of taking the antiderivative, not too bad since we replaced it with u. Now what we need to do is substitute back in. So when we get here, what I want to do is now replace u with our original substitution. So u to the 8, u is equivalent to 2x to the 4th plus 7. So what we're going to have is quantity 2x to the 4th plus 7, all raised to the 8th power, all divided by 8 plus c. And that would be our antiderivative. Then what we could do is you could check your answer with this. So you can always check by taking the derivative with what we ended up with. So if I wanted to check, and I'm just going to switch this around a little bit, I'm going to have it be 1/8 times 2x to the 4th plus 7 to the 8th power plus c. And then what I would do is take the derivative. So plus c is going to go away. This is going to use the chain rule, so we're going to have 8 times 1/8 times 2x to the 4th plus 7 to the 8 minus 1, which is 7. And then we need to multiply that by the derivative of the inside, which is 8x cubed. And we end up with our 8x cubed times 2x to the 4th plus 7 to the 7th power. And that's exactly what we started out with. So that's our substitution method, is choosing something for u so that the derivative benefits us, and it makes it easier to take the antiderivative rather than trying to figure out all of these pieces together at the same time. All right, let's go to this next one, the antiderivative of negative 3x times e to the negative 2x squared. So in terms of looking for an inside function, I can see there's this function inside the exponent there. So what I'm going to do is try out what happens if I let u equal negative 2x squared. If we do that, then if I take the derivative du, we're going to have negative 4 times x times dx. So we're almost there. What I will note is that we actually have a 3 up here instead of a 4, but using some kind of methods with our substitution, we can make that work out. So what we're going to do is start substituting in. So I'm going to have my integral. I'm going to have e to the power of u. And then with du, there's kind of two ways we can go about this. We can try to figure it out as we put the integral together, or we can make some adjustments at the beginning. I was kind of debating between the two, but let's go ahead and make adjustments here. So what I want to do is adjust this negative 4 so it shows up as negative 3. And a lot of different ways to think about this. The way that I kind of like to do it, that is probably a longer format, but it's helpful to see all of it, is that this idea, I'm going to multiply, and what I want to do is get that negative 4 to cancel out. We want to get that out of there and replace it with a negative 3. And there's a shorter way to do this, but I like this idea of, in the numerator, have what we want to end up with, denominator, divide out what we want to get rid of. X is fantastic. We don't want to do anything with x there because we want to end up with x. It's just we want to see a negative 3 instead of a negative 4. Now, whatever we do to one side, we have to do to the other. So what this will do is I have this 3/4 times du is equal to, and then over here with how we set it up, the negative 4's will cancel. So I'd have my negative 3x dx. So little adjustments so that the numbers work out, but otherwise we're all set to go. So now what we could do is, when making our substitution with du, we have this extra piece that we didn't see last time, and it was coming from that fact that we needed to adjust the number. So what I can do is, where I had negative 3x dx, that can now be replaced with 3/4 du. So where I have my e to the u power, I'm also going to have 3/4 du. So we're taking the antiderivative of 3/4 e to the u power du. So much simpler to work with in this form. The numerical part, 3/4, will just stay the same. And when we take the antiderivative of e to a variable, it stays e to that same variable. So we're going to have e to the power of u and then plus c. And then we just substitute back in. So u is the equivalent of negative 2x squared. So we're going to have 3/4 e to the negative 2x squared plus c. So with that, we could check our answer. So pretty much everything would stay the same, but we would have this 3/4 times negative 4x, and that would leave us with our negative 3x. So that all looks good if we took that derivative there. But so with this one, just a little extra piece of needing to adjust du so we can make that substitution perfectly. All right. Here we have the antiderivative of x over the square root of 4 minus x squared. So with this one, in terms of inside function, I'm seeing that 4 minus x squared trapped underneath that square root. So let's try that out. U equals 4 minus x squared. And then we'll have du is the equivalent of negative 2x dx. So what we would have, and what can help us to kind of start seeing pieces come together. So we're going to have antiderivative. We're going to have the square root of u in the denominator. And basically what I need to account for is this x and dx. And what we have is negative 2x. So what we need to do is adjust this so that it's just x dx on that right-hand side of the equation. So to do that, what I would need to do is divide away that negative 2. Or if you want to think of it as we just need a positive 1 there, divide away that negative 2. So it's like we're multiplying by negative 1/2. So negative 1/2 du is the equivalent of x dx. So now we can make our substitution. So let's go a few different ways we can write this. Let's go negative 1 over 2 times the square root of u and then du. So we have our negative 1/2 du is the equivalent of x dx and then square root of u in that denominator there. So we got all of our pieces accounted for. So now let's take the antiderivative. What we could also do here with that negative 1/2 is we could just bring that out front. That might make it easier to deal with. So just take the negative 1/2 out. So then we're just taking the antiderivative of 1 over the square root of u, which is the same as u to the negative 1/2 du. So that negative 1/2 is going to stay out front, and then taking the antiderivative of u to the 1/2, so we'll have u to the negative 1/2 plus 1, which is a positive 1/2, divided by positive 1/2. Okay, so if I adjust my complex fraction there, we'll have, let's see, negative u to the 1/2. That's all those 2's are going to cancel out. So this is a negative square root of u. And with that, we can substitute back in that u is equivalent to 4 minus x squared. So we're going to have the square root of 4 minus x squared with a negative out front. And again, we're used to taking the derivative of complex things. This is all a method of taking the antiderivative of complex things, but when we get to that answer, we can check at the end. Okay, 2 more here. So with this one, I'm going to focus on that e to the x plus 15 that's in the denominator there, that's trapped under that exponent of 3. So let's let u equal e to the x plus 15. And if we go du, then we'll just have e to the x and then dx. This is going to be a nice substitution. I did leave off that dx for that antiderivative there. Okay, so e to the x plus 15, we can make that substitution. So we're taking the antiderivative of u to the third power in the denominator there. And then e to the x dx, that's a perfect substitution for just du. So we're just going to have a 1 in the numerator there and then du at the end. So we're taking the antiderivative of u to the negative 3 du. So we're going to have u to the negative 2 divided by negative 2 plus c. And I forgot my plus c on that last example there. So whenever we take that antiderivative, we should have plus c at the end. Did I get it up above? Good. Okay, so u to the negative 2 over negative 2 plus c, and then we're just going to substitute back in e to the x plus 15. So this is e to the x plus 15 to the power of negative 2 divided by negative 2 plus c, and then I'm just going to adjust this so that it has a positive exponent. So this is going to be a negative 1 over 2 times e to the x plus 15 to the power of positive 2 plus c. Okay, one more here. So with this one, this could be a tricky one to see what the inside and outside function is. So we have x squared divided by x cubed plus 5. One thing that I'll use here though, because there isn't really an inside function, outside function, unless if you think of like the denominator as an inside function in a way, but more what I want to recognize is that if I start with x cubed, when I take the derivative, I'm going to end up with something in terms of x squared. So with that, with u and then eventually getting to du, I'm liking the idea of this denominator x cubed plus 5 as my value for u, so that when I take du, I'm working with x squared. So I'm going to let u equal x cubed plus 5. And then when I go du, that's going to take 3x squared plus 0 dx. All right, so in terms of my values, I have u is going to replace that denominator, so that x cubed plus 5. And then du, I'm almost there. An issue is I have this extra 3 hanging out and I just want x squared. So what we could do is multiply that by a third or divide it by 3 to see that 1/3 times du is the equivalent of x squared dx. So now I can make my substitution for that x squared dx part. So what we're going to have here is the antiderivative of 1/3, or yeah, 1/3 and 1 over u du. So the 1/3 du is coming from du down here, so that x squared dx. And then because the x cubed plus 5 was in the denominator, it needs to stay in the denominator. So that's where I'm getting this 1 over u. So what I'm going to do here is have 1/3 times the antiderivative of 1 over u du. Now the antiderivative of 1 over u is that natural log of the absolute value. So we're going to end up with 1/3 natural log of the absolute value of u plus c. And then we're just going to substitute in x cubed plus 5 for where we had u. So we'll have 1/3 times the natural log of the absolute value of x cubed plus 5 plus c. Okay, so that is substitution method. And again, it just takes some practice of identifying what the inside and outside functions are. But with that, we can take the antiderivative of these complicated pieces. We just need to use u, and really you could use any letter. It's just often called a u substitution, so that we can get to our answer.